Okay, so the first question I want to pose to you guys is, what is a diverging series? Has anyone ever heard of diverging? Does anyone know what it is? What is a diverging series? It's not one we use a lot, but we do or should know the difference between diverging and converging. So anyone know? You're welcome to unmute, or you can put it in the chat. No one. Yeah, like I say, it's not really one that we use a lot in terms of this types of series that we work with in geometric series, but it is useful to know the difference between the two. So hopefully I'll get some more answers for converging series. So guys, a diverging series is basically when you start to add, or when you find the sum, your sum begins to get very, very large. So a diverging series is one where the sum becomes very large. And basically what we mean there is that as we start to find the sum to infinity, so as we find the sum of more and more and more terms, what actually ends up happening is that we get closer to infinity. Now, this is actually not the one that we work with a lot, but it is important to know what a diverging series is. So a diverging series, as we start to find the sum of more and more terms, our sum just gets bigger and bigger and bigger. And so it actually just starts getting closer and closer to infinity. An example of a diverging series is the one I've put down here. So if we have a look at this example, that's right. 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, etc., etc., etc. So if we started to find the sum of those terms, which you can see in this block over here, as we start to find the sum of the terms, what we can see is that the sum just keeps getting bigger. So the sum of the first term, so just 1, is 1. The sum of the first two terms, so 1 plus 2 is 3. The sum of the first three terms, 1 plus 2 plus 4 is 7. And so we keep going. And hopefully what you start to see is that these numbers, these sums, just keep getting bigger and bigger and bigger. And that trend will continue as we start to add more terms. And so this is exactly what I said here. Our sum becomes very large. So that's a diverging series. It's not really one that we talk about a lot. We focus more on converging series, but there are actually two types of series when we get to geometric series, either a converging or a diverging. Like I said, this is not the one we use the most, the converging is, but it is useful to know the difference. Okay, so with that being said, does anyone know what a converging series is? And again, you're welcome to unmute, or you can pop it in the chat. What is a converging series? Mashika, you can ignore my request to unmute. You're welcome to unmute if you would like to give me an answer, but I accidentally clicked unmute on you. I do apologize. No one. Oh, grade 12, slow Wednesday. Alrighty, that's not a problem. So a converging series now is one where, nice, Kanisile, exactly. Basically, our sum starts to get very small and it doesn't go to negative infinity, but what actually happens is we call it, it tends towards a specific value. So a converging series is one where the sum, that's what we're looking at, but anyways, approaches a single value. Now that value can be anything. That value could be 1, it could be 0,3, it could be 40. But what we find is that as we start to add our terms together, they are getting closer and closer and closer to one single value. And Kanisili's comment there in the chat is also a really good way to think about what types of series are converging series. If your terms of your specific series are getting smaller and smaller and smaller and smaller as you go along, it'll be a converging series because you're adding a smaller and smaller and smaller amount each time, which means that those sums are getting closer and closer and closer to a specific value. Right, so there's a little formula that we'll deal with in a second, because like I say, converging series is the one we deal with a lot. But let's first have a look at what series could be a converging series. So if you have a look here on the left, this series that I have of a third plus a ninth plus a 27th plus 181st, plus 1 over 243 is a converging series. Back to Kanisili's point, what we can see is that these terms are getting smaller and smaller and smaller and smaller. We start off with a third. That's a decent chunk. Okay, sorry. That's a decent chunk. There's a third. Then we go down to a ninth, which will be much smaller. Then we go down to a 27th, which will be even smaller. And so we keep going, get smaller and smaller and smaller. And that is characteristic of a converging series. So if we go and have a look at the sum of the series, you can see this over on the right here. The sum of the series, if we start to add our terms up, shows exactly that. So if we just add term 1, that's a third. So that's 0,3 recurring. If we now add a third plus a ninth, that's 0,4 recurring. If we now add a third plus a ninth plus a 27, that's 0,481, 481, etc., etc. Excuse me. And as we start to add our terms, we're getting closer and closer and closer to a specific value. And in this case, our series is converging on the value a half. So as you can see, these values are getting closer and closer to 0,5. And so we say it converges, it approaches a single value of a half. Now, like I said, converging series is the one we're going to work with all the time. I've personally never seen a diverging series question because it's not, there's nothing special about it. That's quite mean, but it's just, it doesn't show this unique relationship of, even though we're adding an infinite number of terms, we only ever approach a single value. And so the converging series is a really important sort of takeaway from this lesson. That's what we're going to focus on. Now, another really important thing to know is that a series will only converge when R is a fraction, basically. It could be a negative fraction, it could be a positive fraction, but essentially when R is a fraction. So I'm just going to write under here, when R is a fraction. So as long as R falls between -1 and +1, you will have a converging series. This makes sense, right? If your R value is a fraction, you're getting smaller and smaller and smaller. Whereas if we go back and look at this diverging series, our R value is 2. I'm multiplying by 2 each time, getting bigger and bigger and bigger. It can't converge. It keeps getting bigger. So this point of the range of R is also really important. And that range, I would really encourage you to remember, because we often ask questions that rely on you remembering that the R value must fall between those two numbers. And we're going to do some questions like that a bit later. So converging series is when it approaches a single value despite adding an infinite number of terms. And really importantly, it is when R is between -1 and +1, not including those values, but greater than or less than -1, +1. Okay, so we've learned about quite a few formulas when it comes to geometric series. We've learned about the TN formula. We learned on Monday about the sum formula. And whilst this is a sum to infinity, we actually have a special formula for sum to infinity. It's a much shorter formula. We don't have to remember, well, it's just a slightly shorter formula, not as many terms to work with in my fraction. But our sum to infinity formula for a converging series is rather S of n, so the sum of n terms. The sum to infinity is equal to a over 1 minus r. A is still the first term, r is still your common ratio, but importantly, as I've said already, your r value must fall between -1 and 1. That is what a converging series is. If it is 3, for example, so if your r value is 3, it's not converging, it is diverging. If your r value is -7, it's not converging, it's diverging. It doesn't fall within that range. So what we're going to have a look at tonight is the applications and the use of this formula. All right, but what I'm going to do is, if you want those little notes, sort of introductory notes, I'll do that, and then we're going to have a look at an example. Okay, so if we have a look at the first example, I've said calculate the sum to infinity of the geometric series a half plus a quarter plus an eighth, etc., etc. Now, guys, because the term values are decreasing, we've gone from a half to a quarter to an eighth, we do kind of know that the r value is going to be within the range -1 to 1, but it's always good to check. And like I said to you before, the first thing that you should always do when given a series or a sequence is calculate the important things, your r value. Go and work out your constant first difference if it's arithmetic. Go and work out the second differences if it's quadratic. Once you have that information, answering questions becomes a lot easier. So for the purposes of this, we are just going to work out r to start off with. So r would be term 2, which is a quarter, divided by term 1, which is a half. And so r in this case is a half. That's great, because remember our range was from -1 to 1. That falls within that range. So the series does converge. And so what that means is, as I start to add an infinite number of terms, it's going to approach a single value. And so now that we know what r is and we can clearly see what a is, all we need to do is substitute that into our formula. So the sum to infinity is equal to a, which is a half, divided by 1 minus a half. Now, Kirsten actually said this on Monday. When you substitute, put it in a bracket. You're going to see later how important it is. So always substitute, or always put your substituted value in a bracket, especially because there is this negative here. It means that the value inside your bracket needs to change sign. So it becomes -1/2. And so if you remember your brackets, it just makes your life easier. Okay, so if you chuck that into your your calculator, get that your sum to infinity is equal to 1. So as we start to add an infinite number of terms in this specific series, we are going to converge on the value, or get closer and closer and closer to 1. So your decimals will be a half, 0.25, whatever 1/8 is. And as you start to add those together, you'll get like 0.7, 0.8, 0.85, 0.91, and you'll get closer and closer and closer and closer to 1. Right, so really not too tricky in terms of just applying the formula, but obviously as we increase complexity in these questions, we need to be mindful of what's happening. Take a quick screenshot if you need to. Otherwise, we're going to have a look at some you-try examples. So Josh has asked, what would the formula be for diverging? So Josh, there isn't a specific formula. We would just use our normal sum formula, which is, sorry, strange things going on, which is that S of n is equal to a times r to the power n minus 1 over r minus 1. So that's what we would use for diverging. Unfortunately, well, I say unfortunately, diverging series, they just get closer and closer to infinity. So there's not a single value that it approaches. So we would just use the normal formula if it was diverging, like we were doing on Monday. Cool. Okay, guys, so you know the drill. Decide where you're at. medium or hard. I'm telling you, oh golly, right, medium or hard, easy or medium. The easy one, you've got 2 2/3, 2/9, and I want the sum of the infinite geometric series. The medium one is -64 plus 32 minus 16, and again the sum. So give those a try. Josh, so there should be a last term for the sum of a diverging. I'm not sure if I fully understand. So technically, no, there won't be like a last value that the sum gets to, because it's just going to approach infinity. Because we don't know where infinity ends, we can't assign a specific value that it approaches. I can say that the series stops after 12 terms and then work out the sum. We did a few examples like that on Monday, but there won't be like a final sum value for a diverging series because it just keeps getting bigger. You can add an infinite number of terms and you will get closer and closer to infinity. So it just keeps going basically. Whereas these converging, because I'm getting smaller and smaller and smaller and smaller, it is going to start to approach a single value, because we're just adding a small little bit every single time. I almost think of it like an exponential. So we're starting off with, let's say, a half, and as we're starting to change those fractions, we get smaller and smaller and smaller, and we approach that asymptote, but we don't quite get to it, but we do converge or approach that singular value. But diverging just goes up to infinity. I hope that makes sense, but let me know if it doesn't. Hey guys, don't forget, you're welcome to put your answers in the chat so that it might help others. My words have just left me. And when you're done, please just give me a thumbs up so that I know. Josh, I just want to make sure that my answers to your questions you're happy with. Otherwise, like I say, just let me know if you're not. Grade 12s, are we good? Like I say, give me a thumbs up when you are done. Just so that I know if you need more time. Thank you, Kirsten. I was a bit worried there that I had just disappeared into the void. Like the answers I'm seeing. Nice, Josh. Okay, thank you, Tapadani. Thank you. I'm going to give everyone a minute and then we'll have a look at the answers. When I do the easy answer, I know it's wrong. So I will correct it. I just made a really stupid mistake. So I will correct it when I reveal it. So don't stress if you see a different answer. Okay, let's have a look. So easy one, like I said, I just made a really stupid mistake because R is not 3. R is a third. And so if I'm not mistaken, this approaches 3. Just make sure my math is right. Yes, okay, so for the easy question, R was a third, so it does converge because it falls within that range. Sub it into your formula and you get that your sum to infinity is 3. So the sum of that series approaches the value of 3. I'll let you take screenshots in a second. If we look at the medium questions, this one was slightly harder because of the negatives. Remember, we spoke about this on Monday. When your geometric series alternates between negative and positive. Oh, sorry, guys. What that means is that your R value is negative because a negative times a negative is a positive. So there's the positive second term. Positive second term times a negative R is a negative third term. So the signs alternate as we go along. So here R was negative a half. And so you got your sum to infinity was negative 128 over 3. Now, some of you I saw on the chat put negative 42,67. That's fine. So we did speak about this on Monday. If you want to round off, it's fine. Obviously, just remember that every time we round off, we're creating an estimate. It's no longer the value in its like pure full form. So a fraction is always better because it's the most accurate form. If you wrote this as negative 42,6 recurring, because it's negative 42,66666, that's also fine. Like I say, you're not going to be marked wrong, but it is the more pure or the more correct form of the answer, leaving it as a fraction. So try as far as possible, but it really isn't the end of the world. All right, so there are the two if you want to take screenshots. And then we're going to have a look at a really cool applications next example of this sum to infinity formula and the sum to infinity concept. Alrighty, so our next example is looking at, like I said, an application of sum to infinity, and that is to convert a recurring decimal to a common fraction. Now, you learned how to do this in grade 10. There was a method that you used where essentially you came up with 2 equations, you subtracted the 2 and you solved for x. You're obviously welcome to use that. But now that we have these geometric series that we can work with, we can apply this new knowledge. So what I want you to notice, and I'm just going to quickly jump back to what we did over here, is that as we started to add terms, so we added the first term, the second terms, etc., we're getting recurring decimals in my sum, and we keep going. Now, because of that nature, because of that pattern that we see, this allows us to create a geometric series with recurring decimals. So if we go and have a look at this example here, we have got 0,3 recurring, and we want to write that as a common fraction. Now, we already know that that common fraction is a third, but let's now actually use the geometric series knowledge in order to show that it is in fact, or in order to actually get that the fraction is a third. So the first thing that we want to check, grade 12s, is how many values are recurring. So how many numbers are being repeated. So in this case, we have got 0,3333, etc. It's only one unique number that is recurring. So you can say how many different values, I suppose, if that makes a bit more sense, or how many unique values. But essentially, it's only the 3 that's recurring. And so what we now want to do is we want to create a geometric series based on this recurring decimal. So that is now going to be our second step here. We now want to create this geometric series. Now, in order for us to do that, we go to our decimal. So this would be my first term, this is my second, this is my third, this is my fourth, etc. Now, you might think, okay, but then my series is 3, semicolon 3, semicolon 3. We need to be careful. This first 3 is a tenth, according to its position after the decimal. This is 100th. This is 1,000th. This is 10,000th. And so its position within the actual decimal needs to be taken into account as we create this geometric series. So we know that this first decimal is a tenth, and so our first term would be 3 over 10. That's 3/10. That represents what that first position after the comma is. Our next one is 100, so it's 3 over 100. There's my 300ths. My next one would be 3 1,000ths. The next one would be 3 10,000ths. We don't really need the fourth term, but that is essentially what we have. So we need to bear in mind where it is in the whole decimal. Is it in the tenths, the hundredths, thousandths, etc.? And that is how we create our series. So once we've created our series, we can now go and find our sum to infinity. Because what's going to happen is that's going to give us our common fraction that this decimal is. So remember, sum to infinity, I need to know what A is. I know what A is, it's my first term, but I need to also know R. So R here would be 3 over 100, so term 2, divided by 3/10, which is term 1, and so R is a tenth. Makes sense? Every tenth, I'm repeating that value, so the tenths, the hundredths, thousands, etc. So it does make sense that my R is a tenth. Now that I have all this information, I go and substitute into my formula. So my sum to infinity is equal to A, 3 over 10, divided by 1 minus a tenth. Again, I'm using brackets for my substitution because I need to remember that sign change. And when you go put all of that into your calculator, you get that your sum to infinity is a third. And that's exactly what we said we should get. We knew that my recurring decimal 0,33333, etc. is a third. And now using our knowledge of sequences and series and specific geometric sum to infinity series, we are able to actually go and work out the fraction. Personally, I think this is a lot easier than the method you learned in grade 10. I just think like algebraically, it's a lot easier. Obviously, both methods are absolutely fine. You get to where you need to be. But we are now able to apply this knowledge that we know from geometric series to convert recurring decimals. So I'm going to stop there, take a screenshot. If anyone has any questions, please do ask. You're welcome to just unmute yourself, or you can put it on the chat as you've seen. Otherwise, we're going to have a look at another example that's still a recurring decimal, but a little bit different, just to see how we would approach something slightly different. Now, grade 12s, I wouldn't stress a huge amount about converting recurring decimals. We'll ask you a question, but it'll be one question. Okay, we're not going to ask you like 5 conversions. If you can do one, you can do one. If you can't do one, you can't do 5. So I wouldn't stress a huge amount, but we probably are going to ask it. So rather bank on 3 easy marks that you know you can get. Right, but let's have a look at the next one. So the next one is now where we have 2 recurring values. So we've got 0,16 recurring. I've just put it like this so that you can see that this line means recurring. So we could have written it as 0,16 with 2 dots on top of the 1 and the 6. The line on top is not a common one that's used, but it can be used. So just so that you know, it does also mean recurring. So the first thing that we want to do, remember, is we want to know how many values are recurring. So in this case, I actually have 2. I've got 16, 16, 16, 16. So I need to be careful here because I can't just now say 1 over 10, 6 over 100, etc., etc. I want to keep my recurring values as a pair. 16 is the recurring number. I need to keep that together. I want to keep that pair together. Valentine's Day. All right, so we just need to bear this in mind. So the second thing that we needed to do is we needed to go and come up with our geometric series. Now, this is where we need to be mindful. I essentially want to figure out what position the second digit is in. So yes, the 1 is in the tens, but the 6, which ends my pairing and starts the next, is in the hundreds. So I would have 16 over 100 as my first term. My second term is now 16 over 10,000, because remember it's 100. Let's try that again. It's tens, hundreds, thousands, 10,000s. My next one would be 16 over a million. Tens, hundreds, thousands, 10,000s, 100,000s, 1 millions. I wouldn't write more than 3 terms. Grade 12, there's no point. Technically you only need 2, but 3 terms is more than enough. And so hopefully what you're seeing here is actually I'm going up every like hundreds, 10,000s, millions. And that's because of the 2 recurring values. But I have my sequence now. And so what that means is I can now use my sum to infinity formula. So we know what A is. It's at 16 over 100. That can be simplified, but like, don't waste your time. You're going to put it in a calculator. Your calculator is automatically going to simplify it for you. Just leave it as it is. R would be the 16 over 10,000 divided by 16 over 100. Again, can be simplified, but your calculator is going to do it for you. That gives you 1 over 100. I just said that we're repeating every hundredths. So that makes sense why my R value is 100th. And now I can put it into my sum formula. So sum to infinity is equal to A, 16 over 100 divided by 1 minus R. Remember, use brackets in your substitution, just in case there's a sign change. And you chuck that in on your calculator. And once you do that, you get that your sum to infinity is equal to 16 over 99. Now, if I just type that into my calculator, I'm not going to bring up the calculator because I'm lazy. Sorry. 16 over 99 on my calculator is 0,1616161616, etc., etc. It does give me my recurring value. And so what's quite nice with these questions is you can check yourself. Type it into your calculator. Do you get the recurring decimal I gave you? Yes, great. No, we've done something wrong. We know we need to go and check our work. All right, so that's essentially how we can apply, and applications of series is one that we do ask you, especially as the sort of complex questions in a test or an exam. So it is important that we can apply our knowledge, but this is how we can apply it to recurring decimals. So let's take a screenshot, and then I'm going to give you two to try by yourself. Similar thing, one easy, one hard. You decide which one you're more comfortable with. And obviously ask me questions as you go along if you're feeling confused. If you have questions now, please do ask. Otherwise, I'm going to move away and give you the examples. Okay. So the slightly easier one is just 0,1 recurring. The medium one, 0,25 recurring. The 2,5 looks a little bit weird. I don't know why the dots are placed like that, but it's 0,25 with the repetition of the 2 and the 5. Right, I'm going to give you 5 minutes. That should be more than enough time. Give me a thumbs up when you're done, please. Remember, answers in the chat. You can help the others. Questions in the chat, or unmute yourself and ask me. But let's give these two a try. Nice, Ati. Guys, remember, you can check yourself. Just put on your calculator. Make sure you do get the correct recurring decimal. And again, just give me a thumbs up when you're done. I see one so far. Okay, I want to go through the answers in a minute, so please remember, thumbs up so that I know you're ready. Thank you, Kaylee. Nice, Josh. Josh, no, it's not the last sum for the lesson. I'm hoping we'll do 2 more, but we might only get to 1 more. But no, it's not the last one. Alrighty, guys, let's have a look. If you're not done, don't stress. You can just grab the answers. So if we have a look at the 0,1, this might be one that you do also kind of know. It's not really one of the common ones, but it is more common than some others. Here we've got the 0,11111, blah, blah, blah. It's only 1 decimal recurring, so you are essentially just working up in tenths, hence why your R value is a tenth. And so you do get that your fraction is a ninth. If we have a look at the medium question, I will make it smaller for you guys to screenshot everything in a second. We've now got 2 values recurring. So we need to bear that in mind when we go and write out our series. We're now repeating in hundreds, so our R value is 1/100, and you do get 25/99 as your common fraction. And again, great tools, put it in on your calculator. Make sure you do actually get the recurring decimal. So just made it smaller for you guys to screenshot if you need, and then we're going to have a look at hopefully 2 more, but we might only get to 1. Alrighty, let's have a look at the next example. So this is now where we see these sorts of questions and then we start to panic because we've got variables, it's geometric, it's a little bit scary, but we don't need to be scared. What we have is p plus p times p plus 1 plus p times p plus 1 squared. And whilst I probably should have said given the geometric series, we hopefully can see that it is geometric. Okay, I know it's geometric because what I see is that I went from no bracket to 1 bracket of p plus 1 to 2 brackets of p plus 1. I'll then have 3, 4, and I'll keep going. So this is now, like I say, where we start to panic because it's variables. So let's look at the question firstly. It says, for what values of p will the series converge? Now remember, we said that a series converges when and only when our R value is between -1 and 1. So if we can essentially use that fact in answering this question, as we've done with all the defining characteristics of our sequences, we are good. So essentially what I want to do is I need to work out what R is and then see if this inequality applies, or essentially sub it into the inequality and see what values P needs to be. All right, so first thing we need, obviously, if we're going to use this whole inequality situation, is we need to know what R is. So we know R is found by saying T2 divided by T1. That would be P times P plus 1 divided by P. Okay. And hopefully what you can see here, grade 12s, is the fact that the P's divide away. So P divided by P is 1. Essentially, that's gone. And so my R value is equal to P plus 1. And now that I know what this R value is, I can just substitute it into my inequality and solve for my values of P. So I will have minus 1. Oh, golly. Minus 1 is less than the P plus 1, which is less than 1. I know what R is. Yes, it's in terms of P, but I have an R value. By substituting it in, it allows me to solve for what values of P. So this is now a grade 10 sort of linear inequality, so we should know how to do this, but just remember, inverse operations tells me that I would need to subtract that 1 in the middle, because remember, I wanted the variable to be alone in the middle. But I would then have to subtract 1 on both sides of the inequality. I can't just do it on one side, I have to do it on both sides. And so what I end up with is negative 2, P in the middle, and 0. So as long as P is greater than negative 2 but less than 0, the series will converge. Okay, so what we've done is we've worked out a range of values that P can be in order for it to converge. So when you are given questions like this, and we like asking questions like this is a question we like to ask. When you are given a question like this, and it's asked for which values will it converge, you work out R. Yes, it'll be in terms of a variable, but you work out R, and then you sub it into your inequality, and you get your range of values. That's it. Nothing complicated. If we then look at question B, it says, assuming the series is convergent, calculate the sum to infinity. So this is an important statement to make, because if we want to calculate the sum to infinity, it has to converge. And it also tells me that I can use my sum to infinity formula. Now, guys, we don't know what P is. We just know P has to be greater than negative 2, but less than 0. So I don't have a value that I can substitute into this original series and get the numerical value of the series. But let's substitute into this formula what we know and see what happens. This algebra is a great thing. So sum to infinity is equal to A. Now your A value was just the P alone, divided by 1 minus the R value, which we know is P plus 1. Now this goes back to what Kirsten said on Monday, what I said again today. Put what you're substituting into brackets. Because what you now need to be mindful of is the fact that this negative 1 coefficient to the bracket has to be distributed into the bracket. And so we get P over 1 minus P minus 1. 1 minus 1 cancels, and so we're left with P over negative P. And P divided by negative P is negative 1. So our sum to infinity here is negative 1. So it did not actually matter that I didn't have my value for P. Through algebra, through solving algebraically, I was able to go and work out what my sum to infinity was. And so even if you're not given a specific value of P, substitute in what you know. Use your algebra knowledge in order to simplify and eventually get your sum to infinity. The important takeaway here, though, guys, is if you want to know in question A for what values of your variable it converges, you need to remember that range, that inequality for R. If you know that, you can use that. Use the information you know about the series you are working with. Alrighty, any questions? Otherwise, I'm going to move on to the last example, which is very exciting. Please take a screenshot before I move. And again, grade 12s, just ask questions if you need. Alrighty. Let's have a look at the last example. So, oh, look at that. Not the last example. That's fine, actually. Let's do the you try. So we've got 6 minutes left. I'm going to give you 4, and then the last 2 minutes we'll have a look at the answers. So all I'm asking you here is for which values of x will the series converge? So basically exactly what we did in question A. So you've got 4 minutes. Let's have a look, decide which one you'd prefer to work with, and then we will check the answers in 4 minutes. Remember, you can put your answers in the chat, might help someone else. I can also then see if we're managing. I'll give you 1 more minute and then we'll have a look at the answers. Nice, Katie. Thank you. Kirsten, thank you. Thank you, Tokozane. Right, if you're not done, don't stress. You can just take screenshots. If we look at the first one, remember I said it's exactly the same as A, so go back in your notes and have a look. But what we want to do is we want to work out what R is. So we take term 2 and divide it by term 1, and that gives us that R is equal to 2x plus 1. And then all you do is you substitute it into that inequality. This inequality that r must be greater than -1 but less than 1. So that's all I did over here, subbed in, and I solved for x. So x in this case essentially needed to be greater than -1 but less than 0 in order for this specific series to converge. If we now have a look at the slightly harder question, we had to do basically a very, very similar thing. What we wanted to do there again was work out r. We got that r was equal to 2 minus x, substituted into that inequality, and we got that as long as x is greater than 1 but less than 3, the series that we were given, this 2 minus x plus 2 minus x squared, etc., will converge. So this one was just slightly harder because of the variables you were working with, and also because grade 12s, in this third last step, you've got a negative x. Now remember, in an inequality, when you divide by a negative, the signs swap. So that's why my signs swapped in the next step. And so we just bear that in mind as you go along. When you have an inequality and you divide or times by a negative, the signs of your inequality switch. And so that's exactly what happened in the second last step. All right, but take your screenshots. If anyone has any questions,